ఈ దిక్కులు చూసుడు ఇక్కడ
Hello. Hello.
Good morning, sir.
Hi, good morning. Yeah, can everybody able to listen me?
Yes, sir.
Yeah, from boys side, CR Ravi. Hello, Ravi. Okay, can you able to listen?
Yes, sir.
Okay. Yeah, I think I can continue. I'm adding 25 number every time I'm adding 25. He or she is not coming. 23, 7. Okay, all of you make yourself available. Okay, not busy or something. An orange symbol is coming. Just make everybody a green symbol available. Okay, today I will start important derivations. A series of 4 derivations will be there. Based on this, many problems are there in the diffusion chapter, nothing but a unit 1. Okay, I sincerely request you to please write down a notes. Otherwise, it is impossible to remember those equations. Only through derivations only it is possible to remember those equations. Otherwise, it is very, very, very difficult to remember those equations. You just follow the class and write down the notes. Then only through a series of steps only you can remember those equations. Many problems are there in the diffusion chapter. You can refer to old question papers also. I have some picks, I guess, old question papers. I will try to keep by today or tomorrow. I will try to keep those in the clips. Who is this 8? Number 8. Sorry, just 1 second. I'm adding somebody else. 25. 8 I have added many times, but he's not coming online. Same with the case 3344. Hello, Ravi. Hello, Ravi. Are you online? Or Isaac? Hello. Anybody is there online?
Yes, sir.
Yes, sir.
Okay. Who is there in online? Okay, I am just raise your hand. I will give a presenter access to you so that you can add somebody else when they come. Who is online? Please raise your hands. Otherwise, just put off your speaker. Put on your speaker and just speak to me. Please make it fast. Make it fast so that I can start class. Okay, 24. I am giving a presenter access to you. Just add when somebody comes in for the next 10 minutes only. After this, just don't add anybody after 10 minutes. Okay, for the next 10 minutes only, you can add. After 10
Sir,
minutes. Mhm.
sir, you can give it to me, sir. 17.
17. I already given to. Okay, I am giving to you also.
Yes,
Just
sir.
my request is to add only for the next 10
Okay.
minutes. Okay,
Okay,
after
sir.
that don't add anybody.
Okay, sir.
Okay. Yeah. I will start the class now. Okay, today we will derive the important derivations in mass transfer operation in the unit 1 diffusion. Okay, those are related to the mass transfer will takes place through molecular diffusion. You already studied, you already understood that mass transfer will takes place through diffusion and convection. In the diffusion itself, molecular diffusion, okay, there are two cases in which mass transfer will take place. The first one among those is A through non-diffusing B, and second one is equimolar counter diffusion. Then what does that means? The about A through non-diffusing B. I think everybody can able to see my live board. So it is steady state according to your syllabus. It is given as a heading steady state molecular diffusion at rest, which is nothing but laminar flow. So in that one, the first case is A through non-diffusing B. A through non-diffusing B. Okay, A and B I am writing in the capital letters here so that you can clearly understand this. These are
Sir, we
from
can't see anything on live board, sir.
yeah, live board is visible to you.
Yes, sir.
Okay, but I am writing here. Just wait a second. I'm making a new live board. Understand why this is happening. Okay, now you can see live board. Z was
Yes,
written.
sir.
Yeah, okay.
Yes, sir.
Thank you. Okay, in this one, the main topic is steady state. I'm just typing. It will come in some time. Steady state molecular diffusion. Diffusion at rest, which is nothing but laminar flow. In that one, the first case will be A through non-diffusing.
ఎక్స్క్యూజ్ మీ సార్, మీరు టైప్
Yes, yes.
చేస్తున్నారా?
టైప్ చేస్తున్నాను.
అంటే ఇక్కడ కనిపించట్లే, అందుకని
ఆ,
అడుగుతున్నా
వచ్చి-
సార్.
లేదు లేదు వచ్చింది, అంతా టైప్ చేసిన తర్వాత వచ్చింది. మొబైల్లో టైప్ చేస్తున్నా కదా అది.
ఓకే
ఓకే
సార్, ఓకే సార్.
ఇప్పుడు చూడండి వచ్చింది కదా.
ఎస్ సార్, వచ్చింది సార్.
Okay, this is the
Chin, sir.
important. Okay, thank you. Yeah, this is the important title. Okay, steady state molecular diffusion at rest, laminar flow, which is nothing but laminar flow. So in that one, the first case is A through non-diffusing B, and next case is equimolar counter diffusion. Okay, first one we will see what is this A through non-diffusing B. So here you can see A through non-diffusing B. What does that means? Okay, A through non-diffusing B means consider a tank, okay, in which a solvent is present. Okay, in this solvent some gas or some liquid is just diffusing, which is composed of two components, A plus B. Okay, let us assume like this, and this solvent is nothing but C. Okay, now what happens when this is a gas mixture? For example, consider A plus B is a gas mixture, okay, in which A is a solute, B is some inert component. Okay, B is some inert component. Okay, then what happens, since A is the solute, when this gas is just diffusing inside this solvent C, then what happens, the B remains constant, whereas A will just impinges or just diffuses into the solvent C. Okay, similarly we can take a real time example. Consider there is a water as a solvent. It is really used in the industrial purposes. Now our A is nothing but NH3, ammonia, and B is nothing but air. When ammonia and air is when in the industrial operation, when we have to separate ammonia from the air and ammonia mixture, we will use composition, a mixture of gas which is composed of NH3 and air is just passed through the water. Okay, it is once again not coming. Okay, when this it is not moving. Once again. Once again, I have to create new whiteboard. Just 1 minute. Just I am creating new live board. Network connection is not good. Okay, consider the real industrial problem in which the main task is to remove NH3 from a mixture of air and NH3 gas mixture. So water has to be used as a solvent. Okay, in this what happens, only NH3 is soluble in water, whereas this air is not at all soluble in water. This is the case of when we consider our A is NH3 and B is air. This is the clearly a case of A through non-diffusing B. A through non-diffusing B. Okay, I think you understood this one. A through what is the meaning of A through non-diffusing B? A through non-diffusing B is nothing but when a gas or a liquid is composed of two components A and B. Only A is soluble in solvent C. Okay, not B. B is completely remains inert. Okay, this is the case of A through non-diffusing B. The real industrial example for this operation is a mixture of NH3 plus air is there, in which our task is to simply separate NH3 using water as a solvent, whereas air is not at all soluble in the water. So this is nothing but A through non-diffusing B. So our title is steady state molecular diffusion at rest, or it is nothing but a laminar flow. In this, the first one is A through non-diffusing B. Have you understood? Have you understood this? A through, what is the meaning of A through non-diffusing B?
Yes, sir.
Okay, yeah. Yeah. Now you understood the meaning of A through non-diffusing B. Oh, once again lost. Just wait, today class already lost. Whiteboard is not at all coming. Hello.
Sir.
Yeah. Okay. My connection lost. Just wait. I'm creating once again live mode. Yeah. Okay. It is working fine. Yes. I'm saying about steady state molecular diffusion, which is nothing but a laminar flow. Steady state molecular diffusion at rest at laminar flow. The first case is A through non-diffusing B. The real industrial problem is when NH3 is getting transferred from a mixture of NH3 plus air. So using a solvent as water, we will separate only NH3 is soluble, but when we consider B as air, it is not soluble. This is nothing but A through non-diffusing B. Non-diffusing B. Okay, this is the example. Real industrial example is NH3 solubilizing in water, whereas air is remains in constant. Okay, we all know for individually for liquids, when we consider a liquid, then we will see the some component properties as well as the total mixture properties. I'm writing in next slide this one. See what are the component properties. For example, I am giving you in a table component. So components are our components A and B, and then next one is mixture. Okay, total mixture. Then what happens to a total mixture? For example, our components are A and B. Then what happens when we mix A plus B? Then total mixture will be A plus B. Similarly, this component will have some mass. Okay, this table is very much important when we deriving the equations. So just please listen to it carefully. So this component A and component B will have some certain mass. This will be denoted by MA, small ma, and small mb. Then what about a total mass? Total mass is nothing but ma plus mb. If we denote a total mass with some m, small m, then m is equal to ma plus mb. This is a total mass. Then this component will have further volume will have when we created a mixture using some solution. When we create some solution, or this component will have individually volume. Density is equal to mass by volume. Then volume is denoted by Va and Vb. Then what about a total volume? Total volume, capital V is equal to Va plus Vb. Similarly, these components will have some molecular weights will have molecular weights. So I am just denoting the notation we can use according to our convenience. Just you have to remember the units and where we have to apply this one. So this component A will have a molecular weight of MWA, and this component B will have a molecular weight of MWB. Okay. Then what about this mixture? In a total mixture, can we write MWA plus MWB, we can't write because it is not a generally additive property. We have to just estimate a average molecular weight. You might have remembered from CPP course, average molecular weight is nothing but sigma xi into mi. We need to specify some composition, some mole fraction molecular weights. So next same table I am just continuing here. B and total mixture. Okay, I'm not writing the main headings. So next is the moles. The components will have some moles. Okay, so this will have so component A will have a moles of which is denoted by Na. Moles is equal to nothing but weight by molecular weight. For since we are writing for a component A, Ma by MW A we can write. Similarly for component B, it is not moving still. Okay, can you able to see the new slide?
Yes, sir.
In which nothing was written, or it is showing blank, or something written?
It is showing blank,
Showing
sir.
blank, sir.
Oh, showing blank. Okay, 1 second, it's gone. Yeah. Okay. Similarly, the same table we are continuing from the previous table. See, first one is component A and component B. It is additive property. A plus B is the total components. Then mass we can write small ma plus small ma and small mb plus b component. Then total mass will be small m, which is denoted by small m, which is nothing but a additive property ma plus mb. Then volume we are in denoting with Va. VA for A component, VV for V component, then total volume V is equal to VA plus VV. Then molecular weight is MWA, MWB. We can write capital M also for molecular weight, capital MA, capital MB. But it is not at all straightforward additive. So we have to use some composition, then only we can write a average molecular weight. You might have remember from CPP course that molecular weight, average molecular weight is nothing but sigma summation of xi, mole fraction or a mass fractions, into molecular weight of individual components. Okay, we can write for similarly for NB we can write moles of B is equal to mass of B divided by capital M I am writing for the molecular weight of B. Then what about the total mixture? Total mixture is nothing but small n, which is total, indicative of total, which is Na plus Nb. Okay, these are the components we can write. Then units of moles are moles. Then units of mass are kg, gram. Then units of volume is nothing but meter cube, liters. Molecular weight will have a units of kg per kg mole or gram per gram mole. Then what about a next quantity? Next quantity is mass fractions. We already described all these in earlier classes, but I am just revising this one in a single table. Then mass concentration. Mass concentration is denoted by rho A. Rho A for A component. Rho A is equal to nothing but a density. Simply when it is individually present, then it is nothing but density. So density is equal to mass by volume, V, total volume. Then similarly for component B, rho B is equal to mass of B by total volume. Then what about the total mixture? Okay, rho we can take for the total, then it is rho A plus rho B. Since this is also a straightforward additive quantity, we can write rho A plus rho B. Then next quantity is molar concentration. Mass concentration we have already written. Then molar concentration. Molar concentration is denoted by C. For A component, it is Ca. This will have a units of mole per meter cube or mole per liter. Ca is equal to mass concentration is mass divided by volume. Molar concentration is mole divided by volume. Na divided by total volume. Similarly, for component B, Cb is equal to Nb divided by total volume. Then what about the total concentration, which is denoted by C? C is equal to Ca plus Cb. Okay, these are the components. Then next one, similarly component A, component B, then total components. Then fractions. Next we have to write a mass fraction. Since we already have a molar mass concentration, then we can write a mass fractions. Then mass fraction is denoted by Wa. Remember this, we can give anything Wa or Xa, depends on our particular context. Okay, Wa I am just writing a variable Wa for the mass concentration. Mass concentration is nothing but individual mass fraction is nothing but individual mass divided by total mass. Individual mass concentration divided by total mass concentration. So individual mass concentration for component A is rho A and total is rho. Then similarly for mass fraction of B is rho B by rho. Then what about total? Total is sum of the mass fractions or sum of the mole fractions is equal to 1. We already know from the additive laws that sum of the mass fraction or sum of the mole fractions is equal to 1. Then similarly for the next component is mole fraction. Okay, mole fraction we can write. Mole fraction is denoted by Xi. Okay, or Xa. For the A component we are writing mole fraction is nothing but individual moles divided by total moles, or individual molar concentration divided by total molar concentration. Okay, similarly for the mass fraction we are writing individual mass concentration divided by total mass concentration. So for the mole fraction, individual molar concentration is Ca divided by total molar concentration is C. Then B is Xb is equal to Cb by C. Individual molar concentration divided by total molar concentration. Then from additive law, sum of the mole fractions of a mixture is nothing but XA plus XB is equal to 1. Okay, this is a molar fraction. Then finally we will have a flux. What about the flux? Flux of component A we are writing Na. Flux will have a units of mole per meter square second. Then for the component B we are writing Nb. Similarly for the total mixture we are writing capital N is nothing but Na plus Nb. Since for your syllabus only two components are there, A plus B, so we are writing for two components. We don't have to bother about the next component B, C, D, E, F. Okay, these components are not at all there in your syllabus. Only two components are there. We are bothered about only two components, Na and Nb. So total N is equal to capital N is just, it is a total mixture quantity, total mixture flux. Na is flux of a component A, Nb is flux of a component B. Okay, these are the components. Similarly for gases, okay, those all the notation scheme for the gases I will just revise once again. See, first we have to start from here. I'm writing a different color. Start from here. First one is component. We will give a component. Then our mixture will contain a components A and component B. Then it will have a total additive properties, or it cannot be added. We have to show that one. So first variable is the component. We are taking what are the components present in our system. Our component has a systems of A and then B. Then what about a total mixture? Total mixture is nothing but a sum of a components present in the mixture A plus B. Then these components will have a mass. So mass of component A is denoted by small m subscript A. Then the mass of component B is denoted by small m subscript B. Then total mass of this mixture is Ma plus Mb. Sum of Ma plus Mb is equal to small m. We are taking this notation. Then this mixture will have some volume. Volume for a component A is we are denoting with Va, capital V subscript A. Then volume for a component B is we are denoting with V subscript small capital B. Then the total mixture volume is nothing but V is equal to Va plus Vb. Then molecular weight. These components will have a molecular weights. Then what are the molecular weight? The molecular weight of component A is MW, or capital M subscript capital A. Then molecular weight of component B is capital M subscript capital B. Then since this is not a straightforward additive property, we can't take capital Ma plus capital Mb is equal to some capital M. Okay, we need to indicate certain compositions, whether it may be a mass concentration, molar concentration, or a mass fraction, or a molar concentration. We already know M average, MW average molecular weight is nothing but sum of the average molecular weight is nothing but sigma xi into mi, or wi into mi. Then these components will have moles, okay, whose composition can be evaluated in terms of moles. Moles is denoted by small n subscript capital A is equal to, moles is equal to mass by molecular weight, Ma small ma divided by capital Ma. Then for the component B, small nb is equal to Mb small mb divided by capital Mb, which is nothing but mass divided by molecular weight. Then the total moles is equal to Na plus Nb. Then next we need to evaluate a mass concentration. Mass concentration is nothing but mass divided by total volume. So mass concentration is denoted by rho A for the A component is equal to mass small ma, which is a mass of component A divided by total volume. Then rho B, which is a mass concentration of B, is Mb divided by capital V, which is volume. Then total mixture mass concentration is rho is equal to rho A plus rho B. Then similarly for the mass concentration, now mass concentration is nothing but which has the units of mole per meter cube or mole per liter. So individual moles divided by total volume. Mass concentration is denoted by Ca, capital C subscript capital A is equal to moles of A by volume, Na by V. Concentration is now C is equal to Ca plus Cb. Further it is not moving. Struck once again. Yeah, okay. Now see, for the mass total concentration is nothing but sum of the individual mass concentrations, molar concentration, Ca plus Cb. And next we will have a mass fractions. We will have mass fraction is nothing but individual mass divided by total mass. Individual mass is W, mass fraction is denoted by W, small w subscript capital A, is equal to rho A is the, here you can see rho A is the mass concentration of A, then total mass concentration is capital rho, simply rho. So individual mass concentration rho is the mass fraction of, rho B is nothing but a mass fraction of component B divided by mass fraction of component, the total mass fraction. Then sum of the mass fractions are nothing but a WA plus WB is equal to 1. Okay, once again it is lost. Yeah, okay. WA plus WB is the sum of the mass fractions, the sum of the mole fraction is equal to 1. This is from CBP, same. Okay, then mole fraction. The next quantity is a mole fraction. Mole fraction is nothing but individual molar concentration divided by total molar concentration. See, individual molar concentration is Ca is equal to Na by V, Cb is equal to Nb by V, and total molar concentration is C is equal to Ca plus Cb. Then same, in molar fraction is nothing but this is individual Ca concentration divided by total molar concentration. For B is Cb divided mole fraction of A is equal to, once again not very much. Yeah, individual, he can see here individual CB by C is equal to XB and CA by C is equal to XA. So same we are writing here, XA is equal to XB is equal to, then sum of the mole fractions is equal to 1. Then similarly for the fluxes, flux for A component is Na, flux for B component is Nb, and flux for total components is N is equal to Na plus Nb. Similarly, same with the cases of gases we have to go. Then the gases, for the gases, instead of concentrations, we will evaluate pressures, because gases will exert pressures. Then measuring pressure will directly indicate the volume of particular gas in that composition, and the same time moles. Why? Because for gases, volume percentage is equal to mole percentage is equal to pressure percentage. Okay, this is also from CPP course. You already know, for the gas volume percentage is equal to mole percentage is equal to pressure percentage. When we evaluate volume percentage of a particular gas, we can calculate mole percentage. When we evaluate pressure percentage, we can calculate moles percentage. So for the gases, volume percentage is equal to mole percentage is equal to pressure percentage. Using this law, we can state, for the gases, instead of evaluating concentrations, we will concentrate on finding pressures. So pressures are the indicator of molar composition or composition of a gas. For the component A and component B and total So we have to write what for the partial pressure. So since this is a mixture, we have to write a partial pressure of A. So partial pressure of A is denoted by PA bar. Then partial pressure of B is denoted by PB bar. Then what about the total pressure? Total pressure we are indicating with PT. Total pressure is equal to PA bar plus PB bar. Okay, this is a total pressure. Similarly, we can calculate the concentration. When we evaluate pressures, we can calculate the concentration from ideal gas law. From ideal gas law, what is the concentration? Ca is equal to PA bar by RT. How it is? It has come. I will show that one. So Cb is equal to PB bar by RT. Then similarly with the total concentration is we are denoting with total concentration C. C is equal to Ca plus Cb, which is equal to PT, total pressure divided by RT. Okay, which is also equal to PT by RT, total pressure divided by RT. Okay, these two quantities. Then what about the mole fractions? Okay, I am writing in the next slide. Okay, then same, we need to write mole fraction for gases A, B, and this is for total. Then what about a mole fraction of gas? Mole fraction of gas is denoted by Y. So since this is a Ya, we have to write Ya is equal to individual concentration by Ca by C. Then Yb is equal to Cb by C, or else we can write PA divided by PA bar divided by RT divided by PT divided by RT. RT will be cancelled out, so left out terms will be PA bar divided by PT. So similarly for the total mixture, Ya plus Yb plus Ya or Ya plus Yb is equal to 1. Sum of the mole fractions is equal to 1. So we can write this also equal to Ya is equal to PA bar divided by RT. Since Ca is equal to PA by RT, then total concentration is PT divided by RT. Then RT is cancelled out. Then left out terms I am writing here. Ya is equal to partial pressure of A divided by total pressure. Okay. Then Yb. Then Yb is equal to, similarly Yb is equal to PB bar divided by RT divided by total concentration is PT divided by RT. So RT will be cancelled out. Left out terms will be partial pressure of B divided by total pressure. Okay, these are the notation schemes. Just remember what are these notation schemes, so that in the next class we will derive. Okay, today we wasted much class, so just watch this video once again. Just concentrate on what are the notation schemes involved. What is Ya, what is Xa, what is WGA, what is Ca, what is C, what is partial pressure of A, what is partial pressure of B, what is total pressure, whether the total pressure is additive quantity, whether that partial pressure is additive quantity or not, whether that mole fraction, sum of the mole fractions is equal to 1, why not it is small x. Okay, you just need to understand those concepts, then only we can start the in the next class clearly what is the derivation. I will show the easy way to derive those equations. Just you can remember this table. You have to remember this table so that you can derive easily that equations. The 4 equations will be there, which are very important as per the examination point of view, at the same time for the problems also. So just concentrate on this table and notation scheme. You have to grasp the notation schemes, what are the notation schemes involved. Then only you can able to know how the derivations will be carried out. Okay, I will just take attendance. In the next class, same CT1 is there, CT2 is there. Today I will take mass transfer in that class. 5th hour also mass transfer I will take. So just give me your attendance. 17, 19, 20, 16/24. Okay, please quickly give your attendance. I will mark absent otherwise. 16/24. Okay, absent. 17/32. 17/32.
Sir, yes, sir, yes, sir, yes, sir.
ఏం చేస్తున్నావు?
సార్ నేను మైక్ టర్న్ ఆన్ చేస్తున్నాను సార్, అవ్వట్లేదు అది.
ఓకే రైజ్ హ్యాండ్ అన్న రైజ్ చేయి లేకపోతే త్వరగా
Yes, sir.
32 17 batch 32 ఓకే హీస్ absent 18 batch 1
Present, sir.
3
Present, sir.
4
Present, sir.
5
Present, sir.
6
Present, sir.
8 8
Present, sir.
9
Present, sir.
11
Present, sir.
13
Present, sir.
15 15 okay 15 absent 8 22 22 22 absent 26 26 okay 22 6 present 27 29
Present, sir.
30 30 30 last time okay absent 30 32
Present, sir.
33
సార్ మీరు 22 చెప్పలేదు సార్.
Present, sir.
33
Present,
33
sir.
34
Present, sir. Present, sir.
36 36 36 okay 36 absent 44
Present, sir. Present, sir.
47
Sir, Ati present, sir.
47 47 last time okay absent 49
Present, sir.
okay who is this DCT 33 he's on
Sir.
hold
సార్
hmm.
22 అడగలేదు సార్ మీరు.
ఓకే వీడియో ఒకసారి మళ్ళీ
30,
వాచ్
sir.
చేయి వీడియో మళ్ళీ ఒకసారి వాచ్ చేయి నేను అడిగానో లేదో అర్థమైంది వీడియో మీకే వస్తుంది
Sir, 30 present, sir.
17
17 series 32.
ఓకే వీడియో ఒకసారి వాచ్ చేయి అప్పుడు ఎందుకు పర్లేదో అర్థమైంది ఓకే బాయ్
Okay, good morning, students.
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am. Yeah. So, some more are there to be invited? You 19 are there. Huh? How it happened 19? 19 since students are there. They were not there in the first hour, huh? Please reply. Yeah. Acha, it's continuing.